Hi everyone, today we're going to begin Unit 10 on energy and thermochemistry, which is the first of 2 units on this particular topic. We're going to begin just with maybe trying to have a better understanding of what energy actually is. And according to William Blake, he says energy is eternal delight, which is great, but if we want a more scientific understanding, getting an exact definition is not always easy. A lot of people will define energy as the capacity to do work, which sounds great, although in chemistry, as we will see, we're going to be interested in a lot of chemical reactions where energy is transferred from one form to another without any work being done at all. So yeah, you can define it in terms of work, but that's maybe not the only way to define it. Richard Feynman, Nobel Prize winning physicist, says, "It's important to realize that in physics today we have no knowledge what energy is. We do not have a picture that energy comes in blobs of a definite amount." So it's one of these concepts that is a little bit difficult sometimes to completely and fully understand or completely and fully define, even though there are multiple definitions out there. So we're going to hopefully develop a feel for what energy is and how it what the implications of this might be in chemical reaction. So we know energy, first of all, comes in a whole bunch of different forms. Thermal energy, electrical energy, nuclear energy, chemical energy, and so on, and that we can interconvert it, generally speaking, between each of these forms. Not all of these forms will be necessarily relevant to most chemical reactions we're going to be looking at. One form of energy, which is very important in chemistry and physics, is what we call kinetic energy, which is energy associated with an object that it possesses because of its motion, because of its velocity. And we can actually define this mathematically, saying kinetic energy is 1/2 of the mass of the object multiplied by its velocity squared. So of course, an object that's heavier will have higher kinetic energy than a lighter object that's going the same velocity, and the energy increases with the square of the velocity. So the more you speed it up, the much more energy that it will have. We can say that atoms have kinetic energy because atoms are constantly moving. They're constantly, especially in a gas, they are careening off each other. They're hitting the walls of the container. These particles will each particle will contain its own kinetic energy. Potential energy is another broad form of energy, which is just energy that is stored in an object or associated with an object as a result of its position. So we could say that, for example, we have a waterfall here, that the water at the top of the waterfall would have higher potential energy than the water down below. And that if the water falls off the edge, what happens is it will convert some of that energy into some of that potential energy into kinetic energy, so the water will accelerate as it plummets down. So we could say that in chemical systems, potential energy is very important as well. We could actually say a bond is a form of potential energy, the energy associated with bonding, because it's the amount of energy depends on the position of one atom relative to another atom. So it's not associated with motion, it's associated with position. So that's really the two broad forms of energy that we're going to be most interested in a chemical system. We often say, we have this idea of something called chemical energy, that if you look at something like, dynamite, if you light the fuse here, you're going to get an explosion, and people might say, well, that's chemical energy that's taking place there. Really what this is, it's a form of potential energy associated with the chemical bonds of the molecules that are inside the dynamite in this case. Now, often you might hear in biology people say that bonds store energy, and that photosynthesis absorbs light energy from the sun and stores it in chemical bonds. That's actually not a correct way to think about it, because by definition, a bond is always an energy minimum. that if you take two atoms and you put them together to make a bond, the result is going to be lower in energy than the two atoms were at the beginning. So every time you form a bond, you're always releasing energy, not storing it. You're not putting it away. You're releasing it in some other form. When you do a chemical reaction, like set off dynamite or burn wood or something like that, certainly there's energy in that system that does get released to the surroundings, but it's not because you're breaking a bond and releasing energy. It's actually because you're forming bonds that are stronger. It's the product bond formation to make things like carbon dioxide and water that is releasing the overall energy that we're seeing released in that chemical reaction. Okay, for units, we have a bunch of different units that we typically use for energy and some conversion factors that are important here. Joule is certainly the most important one. It's the SI unit, it's the preferred unit to express energy. Another one that's actually fairly commonly used in chemistry is the calorie, and this is a bit of a archaic unit, but you still actually find it in publications and books, particularly in organic chemistry. And it's equal to 1 calorie is equal to 4.184 joules, so there's a conversion factor right there. When you buy food and it has energy printed on the package in calories, they always use capital C calories, which is actually a kilocalorie, which is 4.184 kilojoules. So that's what that means. And then the rest of these are just other conversion factors between joules and other units. All right, so we're going to begin this unit talking about the first law of thermodynamics, which states that energy is always a constant through some chemical process. That energy cannot be created or destroyed. And when I say chemical process, really any process, any chemical or physical process takes place, whether it's a nuclear bomb, whether it's a chemical reaction, energy cannot be created out of nothing, and it cannot be destroyed. It cannot be made to disappear. All that can happen is that energy can convert from one form to another form. Actually, one thing that we see is that when you have a nuclear reaction, what's going on there is we're actually either turning energy into matter or mass and turning mass into energy. So from that perspective and the perspective of the first law of thermodynamics, we can imagine matter itself, mass, as being a form of energy. And when you think of it in that perspective, certainly the first law of thermodynamics still holds. So we would say the change in internal energy of the universe is always zero, always a constant. Energy may flow from the system to the surroundings or vice versa, but the sum of them is always a constant. You can't make energy appear out of nothing. This is just a light switch that was up in the physics hall here. It says, please turn off lights, conserve energy. And yeah, energy is always conserved. All right, I just talked about system and the surroundings and maybe got slightly ahead of myself here. Basically what we do when we want to analyze the energetics of a chemical system is we like to divide the universe up into two parts. There's the system, which is the piece of the universe that we are interested in studying and investigating, and then there's the surroundings, which is everything else. The system itself could be a reaction flask and the contents of that reaction flask. It could be your body, your whole body is a system, and everything outside of you is the surroundings, if that's the way you want to look at it. It could be a cell. It could be any defined part of the universe. It could be a house. It could be almost anything. Hi, just had to take a quick break. I got a call from a scammer, so I had to deal with that. Back though. Right, so we define the system and the surroundings. System is the part of the universe we're interested in. The surroundings is everything else put together. If you add them together, you get the universe. Chemical systems can be in a number of different forms. We can define these as such. We would say that an isolated system is the one on the right. It's one where energy cannot be transmitted from the system to the surroundings or vice versa. So we might say that might be like a a thermos, where a thermos is insulated, it prevents energy transfer in or out. Not that there exists a thermos that's perfect at doing that, but theoretically at least. It's also isolated, also means not only is it thermally insulated, but it also prevents matter from going in or out of the system. So it's like a flask that has a cap on the top, so you can't have matter, gas go in or out. A closed system is one that prevents matter from transferring in or out, but allows energy to go in or out without any trouble. In an open system, matter can go in or out, and energy in the form of, say, heat or light can go in or out as well. So yeah, those are the three types of systems that we can imagine. Our bodies, we could say, are probably an open system because we can absorb or emit heat from our bodies. Generally, we're emitting heat because we're typically warmer than our surroundings. And we can also exchange matter with the outside world because we're constantly breathing in and out, and we can eat and so on. So we're an open system. Now, in chemistry, when you do a chemical reaction, we usually concern ourselves only with two different forms of energy, and this is energy that's exchanged between the system and the surroundings in the form of heat and in the form of work. Now, these aren't the only two ways that a chemical system can trade energy with a system. It can also be light, for example. You could have a reaction that absorbs light, like photosynthesis, or one that emits light, which would be called chemiluminescence. But for the purposes of this unit, we're going to simplify things and only consider heat and work. Heat is just energy transferred between two objects that are at different temperatures. And we sometimes call this thermal energy. And thermal energy is a form of kinetic energy because it's the energy associated with the kinetic movement of all of the different particles in that sample. And the faster they're moving, the greater the amount of potential energy is in there. So thermal energy you can think of as basically like the sum of all the individual kinetic energies of all of the particles making up that material. Work is energy associated with moving or motion against a force. So, if you lift something up from the ground, you're moving it against gravity, which is the force pulling it down. So that would be, it would require work or energy in the form of work to accomplish that. So we sometimes design physical systems to maximize the amount of work that can be done in a chemical reaction. Like an engine of a car, you want to convert the chemical energy, of the chemical energy of the combustion to do work, to move the wheels, push pistons, which will make the car move forward. So when you think of a chemical reaction, it can either absorb or we can think of it as either absorbing work, meaning the surroundings are doing work to the system, or doing work, which means it's doing work against the surroundings. And this may be easy to understand in a piston, like if you have a sealed container with a cap that's movable so that the contents, the system here can expand or contract. If you have a reaction which is producing a gas, it will cause the piston to push up against atmospheric pressure. So that would be an example of the system doing work on the surroundings. Or you could have a reaction where a gas is absorbed, which would be like the reverse of this particular reaction. And in that case, the system is being compressed. So we can think of that as work either being done by the system to the surroundings, or work by the surroundings being done to the system. In both cases, we're associating this with a change in volume as a result of a change in gas particles. Either gas is being formed or a gas is being absorbed in a chemical reaction. So we can define work mathematically as equal to the external pressure times the change in the volume of a chemical reaction. And the sign of work can be positive or negative. It depends on if work is being done to the system or by the system. And with that positive or negative value, think about, does the system absorb energy overall? And if that's the case, W is positive. So when work is done on the system, you can say the system is absorbing the energy in the form of work that's being done to it, and the value is positive. If the system is expanding by producing a gas, it's doing work to the surroundings and losing energy, or it should have a negative sign for work in that situation. Right, we looked at that example already. Okay, so here's an example of a chemical reaction that absorbs a gas. If you take calcium oxide and react it with CO2 gas, that will produce calcium carbonate solid. And so in this case, we would say that the change in number of moles of gas is -1 as a result of this. And as a result, we would expect the surroundings to be doing work on the system. The system is absorbing energy from the surroundings, and W is going to be positive. So our equation for work as -P external times delta V, we can also express that in the form of delta N gas times RT, because we know from the ideal gas equation that PV equals nRT. So that these two are equivalent ways of talking about, don't need a software update, equivalent ways of quantifying the work done by a chemical reaction. Look at an example. For the following reaction, we have 120 grams of CO2, which is captured by excess calcium oxide at 1 bar of pressure at 298. Calculate the work. All right, so to handle this particular question, the first thing we want to do is take our mass of carbon dioxide, which is in grams, and convert that to moles, because we want to do this whenever we do any kind of chemical equation which is involving some level of stoichiometry. We want it in moles. Why don't we do that up top, leave ourselves some space. So moles of CO2 is going to be equal to the mass of the CO2 times the molar mass of CO2, which is 120 grams 3 sig figs over the molar mass of CO2, which is 44.01 grams per mole. And 1 sig fig more than the mass that we have is certainly plenty here. And that gives us 2.726 moles. Now I'm carrying one additional significant digit here, which we can round off right at the very. All right, so the easiest way to probably do this is use the second form of the equation here, where we know that the amount of work equals negative delta N, and we realize that the number of moles of gas of CO2 of 2.76 is that's being lost, that's being absorbed by the reaction. So we could say that the delta N is negative 2.726 moles multiplied by R, which is 8.314 joules per k mole, multiplied by the temperature here, which is 298 degrees Kelvin. And if you calculate this out, you end up with 6,755 joules, which is 6.76, we'll say, kilojoules, rounded to the correct number of significant figures. So notice that this value is a positive value, which suggests that the system is contracting in volume, that it's absorbing work from the surroundings. And that's exactly what is given to us if we use this equation correctly. All right, one thing that I want to just reiterate, heat we talked about is the thermal energy transferred during a chemical reaction, and we looked at this as being a form of kinetic energy. We would say that exothermic reactions are ones that release heat to the surroundings, so Q will be negative. So we use the same sign conventions for heat as we do for work. If energy is leaving the system, which is in the case of exothermic reactions, it gets a negative value. If energy is entering the system, which is in the case of endothermic reactions, they absorb energy from the surroundings, Q is positive. Q is the symbol we use for heat. I want to distinguish between heat and temperature, which is two terms which are different things but are commonly confused. Temperature is just the, I guess you could say, it's the average kinetic energy of the particles of a system. It's what we call an intensive property, which means it does not depend on the size of the system. So an example here, this person who's in the hot tub has a cup of coffee. You could imagine that the water inside the cup of coffee, or the coffee itself, can be the same temperature as the water in the hot tub. So even though they're very different volumes, they can have the exact same temperature, whereas we would say the heat that is stored, I guess, in the coffee would be a much smaller number than the heat stored in the tub. Or another way to put that is the heat required to raise the temperature of the coffee in the mug by 10 degrees would be way less than the heat required to raise the temperature of the hot tub water by 10 degrees. So extensive would be heat, and intensive would be temperature. Extensive just means it depends on the size of the system, the magnitude. So heat is a form of energy, just like work. It's measured in joules, just like work, and it's given the symbol Q, whereas heat is given the symbol, work is given the symbol W. So if you look at a particular system, we could say that through a chemical process, the internal energy of the system is the sum of Q and W. And this is ignoring all the other kinds of work like light, which sometimes happens, and maybe electrical energy and so on. But for a chemical reaction like burning a piece of wood, really all we're worried about is Q and W. And we can add those together and get the change in energy of the system. So if you think about this, many reactions that we do are done under what are called constant volume conditions. So if you have a reaction going on in an aqueous solution, for example, that does not produce gas, like let's say you have, I don't know, two metal ions that are in there and they do a metathesis reaction or something like that, we would say that the conditions there are constant volume. The volume isn't changing here, and therefore the work being done is zero. The volume's not changing, you're not doing any work, and therefore the entire change in energy of the system is associated with the heat change. So we have this little subscript V, which indicates that under constant volume, the Q for a constant volume process is just equal to the change in internal energy of that system. So that's actually important in many biochemical reactions as well, because you think of reactions taking place inside cells. Generally speaking, those cells aren't changing their volume, so work is not being done. Work is often, in cases like this, something that we can ignore. Here is another example. The temperature of 1 mole of a liquid is raised by heating it with 750 joules of energy. It expands and does 200 joules of work. Calculate the change in internal energy of the liquid. Okay, so we have this 1 mole, and we are raising its energy, raising its temperature by heating it. So Q is going to be equal to 750 joules, and we have to consider if this is a positive or negative value. So we would consider this a positive value because the system, which is the liquid, is absorbing energy from the surroundings. It expands and does work, and so the work is going to be 200 joules. Positive or negative? Well, if the system is expanding, it's doing work on the surroundings, and so it's losing energy to the surroundings in the form of work. So that's going to be a negative value. So the change in internal energy is just Q plus W, which is 750 joules minus 200 joules, which is equal to 550 joules. So overall, the system is still gaining energy from this particular example. Now, one thing that we find is that if you add thermal energy to a system, the temperature change that actually takes place depends on the substance itself. So what we find, if you take something that's pure gold, like this particular coin, and something that's pure copper, like this old scent, what we find is that it takes roughly 3 times more heat to raise the same mass of copper by 1 degree than it would to raise this temperature by the same amount for the same mass of gold. So in other words, copper will absorb a lot more thermal energy or heat from the surroundings than gold will for a comparable change in temperature. And this is true, honestly, you take any two substances, there's actually very wide variations in the amount of energy they can absorb without changing their temperature by that much. We can calculate this number. We can say that an object will have a certain heat capacity, which is just the amount of energy in the form of heat that it can absorb before it raises its temperature by 1 degree. So we have this equation, Q equals capital C delta T, that the energy absorbed or emitted is equal to the heat capacity of the object multiplied by its change in temperature. Something else that we often define, which is related, is something called specific heat capacity, which is small c subscript s. And this is if you have a homogeneous substance, something like pure copper, pure gold, pure water, pure oxygen, whatever it is. It's the amount of energy that pure substance can absorb per gram in order to change by some specific amount of, change its temperature by a specific amount. So we could say that the small cs, specific heat capacity, is the amount of heat that's absorbed divided by the mass of the sample and the change in temperature that's observed, which gives us units of typically joules per kgram. So we would use heat capacity, capital C, when we're looking at a system which is not maybe a pure material. Maybe if you had, I don't know, the heat capacity of our body is not a pure material. It's got all kinds of things. It's got blood, it's got bones, it's got muscles, fat, all sorts of different things. So when you have an object where you want to define the entire object, you'd use the capital C. If you want to talk about heat capacity per amount of material and it's a pure substance, then we can use specific heat capacity. And we end up with these tables which show us specific heat capacities for many different substances. We have copper here, we have gold, water, marble, sodium chloride. Notice here that copper has roughly 3 times the heat capacity of gold, which we talked about earlier. Water, though, is like 10 times higher than copper. So it takes 10 times more energy to raise water by 1 degree Celsius than it does to raise the equivalent mass of copper by the same amount. So this means water is actually a fantastic absorber of energy without changing its temperature by very much. You often see in high-end computers, like people that like to play a lot of PC games and they have a gaming computer, the processor can give off a lot of heat, which if the temperature goes up too high can damage the computer or cause it to shut down. And so what often happens is we use a heat sink, which is a big block of typically some metal, which can absorb that energy. And what you want is something with a very high heat capacity so it can absorb a lot of energy without getting too hot. In the really top-end systems, you sometimes see water-cooled systems where there's water that's flowed through, and water has a much higher capacity at absorbing that heat than any of the other things that you see on this list. So let's do an example. How much heat in kilojoules is needed to bring 1.5 liters of water at room temperature to its boiling point? Okay, so what we want to do here is first of all calculate delta T, and that's going to be T final minus T initial, which is the final temperature is its boiling point, and its initial temperature is 21 degrees C, which is 79 degrees C, which actually works out to be the same thing as 79 degrees K when we're talking about a change in temperature, when we're talking about a delta T. The mass of water is 1.5 liters, which is equal to 1,500 grams, because we know the density of water is 1.00. And then we can say that the heat that's needed to bring the temperature of this water up, Q, equals mCs delta T equals 1,500 grams times 4.18 joules per kg times the delta T, which is 79 K, which is equal to, we're in units of joules, 495,330 joules, which is way too many sig figs, 495 kilojoules. So that'll be the exact amount of heat, amount of thermal energy required to bring that volume of water up by that amount. All right, that's it for this unit. We're going to continue before we get too far.